Okay, helium burning star. So helium burns in the core, hydrogen burning in the shell, and while that's happening, the star is going to go through that phase more rapidly because it gets less energy out of helium burning, and it therefore will evolve quickly. The helium burning is still a powerful fuel, and because the inner core rather has gotten so much more dense, the luminosity, the energy output of the core, is actually going up, and going up fairly rapidly. And so stars spend almost their, so here's what the sun will do. The sun will spend almost its whole life right here. It'll slowly migrate up, very slowly. Here, I guess we start here at the zero-age main sequence. Very, very slowly, billions and billions and billions of years going by, and then it starts happening a lot quicker, going up here to the red giant area. So when the sun becomes a red giant, it's going to bloat out. It will swallow up the orbit of Mercury and Venus and almost the Earth. Now, it's not that the sun has gotten more massive. It's, in fact, gotten less massive. Oh, well, it's just kind of a cool little local thing. So I happen to be the discoverer of what was the most intensely spotted star ever seen. That's HD 12545. And it had a star spot on it that covered half the star. And it kind of blew a lot of astronomers away. But other observatories got on it after I made the initial announcement, the discovery using equipment right here at Cabrillo College, and confirmed it. And so star spots can be surprisingly large. Anyway, this is a red giant, subgiant really, and just a little point of interest. Okay, I'm going to skip that. Okay, so what happens down here is there's kind of two stages to this, you see. So the core collapses. It makes the outer envelope expand because what you're doing is you're releasing gravitational energy. Finally, the core gets so dense that it actually ignites what we call the helium flash. And a lot of the helium, or a reasonable amount of the helium, all goes up at once, fuses to carbon. So much so that it actually expands the core so much that it shuts off the nuclear burning. And then the star actually migrates back down in luminosity till gravity takes over again, it climbs back up. So now we have helium burning in the core, and then we've got shell burning of hydrogen. And if you have an even, well, this is the evolution of the sun. So for the sun, that's the end. Now, what will happen at the very end is the last stages of burning tend to be a bit unstable, and the outer envelope is so big and so gravitationally poorly attached that it's pretty easy to just lift it off. And so what happens is it does lift off. That bloated red giant shell lifts off, and revealing now down at the center a tiny little object called a white dwarf, a newly dead star, which is the core of this ancient red giant. The star's dead, but it still glows. Just like when you die, you'll stay warm for, I don't know, maybe an hour. But these guys are extremely dense, and they have very tiny surface areas, are only the size of the Earth, and so they cool off extremely slowly. They will continue to glow for billions of years, not just an hour. Now, when you first see the white dwarf, it's going to be way over here, extremely hot. It's going to cool fairly quickly because now it's exposed to the cold of outer space. And it's going to drift down here like this and end up in what we call the trash bin of the HR diagram, where the white dwarfs are. We'll see that a little bit better maybe in a later slide. Okay, I'm going to let you read that on your own. Again, this is a purple slide. Remember, purple slides are kind of a little extra beyond the usual. Not holding you responsible for that. But this is a nice diagram showing that what the star does is it kind of develops like an onion, and you end up with these cores. So here's carbon to oxygen fusion, and then helium to carbon burning, and then a helium layer, and then hydrogen burning still going on in the shell. So there's inert layers, and there's burning layers, and there's more inert layers, and the star is kind of growing from the inside out like an onion as these new chemical fusions are enabled by higher and higher temperatures and densities. I'm not going to talk about the S, R, and P process here. You can read about those on your own. You know, it's a lot of complicated nuclear physics, but basically neutron capture and then beta decays, because those are energetically favorable to make a more stable nucleus, and you kind of wander your way up and over till finally you find your way to a chemical element that is stable against any kind of radioactive decay, and then you just sit there. So look at the evolutionary timescales for something like the Sun. It's a main sequence star for 11 billion years. It's a red giant for only 1/10 of that. It's an asymptotic giant branch star for only 1/10 of 1/10, so only 100 million years. An asymptotic giant branch star for only 20 million years. And it goes through these thermal pulse phases. Well, the Sun's only going to go through one, but for less than 500,000 years. Planetary nebula is only lasting about 10,000 years. This is one reason why planetary nebulae, they're called planetary nebulae, because these little ghostly shells that surround stars are small and greenish initially, and they look kind of like the planets Uranus and Neptune. There's only a few hundred of them known in the galaxy, and it's because the amount of time that this shell is bright enough to be visible is very short. Compared to the 11 billion year age of the galaxy and stars like this, we're talking about only 10,000 years, so you know, a millionth of the age of a star. And then look at the mass. Look at the mass of a solar type star when it finally dies. Half the mass is gone. Where did it go? Well, it got blown off during the time it was mostly a red giant, and then even more so with these later phases. Even now, the Sun, though, has a solar wind, so it is gently losing mass. But the more bloated it gets, then the stronger the stellar wind, and the faster it'll lose mass. So there's the evolution of the Sun. Notice the time scale down here. Here's 12 billion years. Let's do that again. From here to here, 12 billion years. From here to here, only 300 million years. And then from here to here is only, I don't know, it's hard to figure. What is that? A thousandth of a billion years? So, 1 billion years, something like that. So obviously stars go through big changes only at the very end of their life. And we're all doomed. Okay, but you already knew that, so let's go on. I don't think I'm going to click on the web simulator. I'm going to let you do that. You can play around with it and watch how fast stars evolve on the main sequence. I do want to talk briefly about carbon stars because they're pretty cool. If you think about the helium burning to make carbon, then you may ask, well, okay, but then we're made of carbon, and the Earth has carbon, and plants are made of carbon. How'd that carbon get here if what you're telling me is the white dwarf sounds like it's mostly made of carbon at the end, and it's not going to get out. It's going to just sit there. It's going to, be part of this stellar corpse. Yeah, that's true. So most of the carbon that gets made never gets out. If it doesn't get out, it's not going to be any good for creating life forms like you and me. So we have to be very grateful for a certain kind of star called carbon stars. Carbon stars are red giants which have very deep convection zones. Their convective instability zones extend all the way down into the core where the carbon is made. And so they are actually able to dredge freshly made carbon that they've generated all the way to the surface, where stellar winds then carry it away from the star. It cools, and then the carbon combines with carbon and makes little graphite grains. Okay, so graphite grains and also carbon monoxide. It's another thing that's made. Carbon and oxygen are right next to each other in the nuclear burning sequence, so you get a fair amount of carbon and oxygen, typically, in all this. So these graphite grains are the most common form of interstellar dust. And they're kind of like the Pigpen character in the Peanuts cartoon. They shroud themselves in their own dust, reddening the star dramatically. So carbon stars are kind of cool. If you get a chance, again, to take one of my field astronomy classes, then I'd urge you to go. I always try and find a carbon star to look at because they're so pretty. They're a deep red, ruby red color, and they're the reddest of stars out there, and it's because they're not only cool and therefore red from thermal radiation, but they're enhanced reddened because they're having to shine out through their own dust. So there's a carbon star, photograph from the 2-mass survey. Notice how red that is compared to ordinary white dwarf. Not a white dwarf, ordinary white main sequence star. So maybe you should remember, actually. Where are we? Here we are. The Cepheids, classical Cepheids. They're named after the prototype star Delta Cephei. These are pulsating stars that are extremely useful because their period of pulsation is tightly correlated to their luminosity. So they become great standard candles, and they're also way up here at the top of the HR diagram. They're among the brightest of all stars, and therefore you can actually literally see the individual Cepheids in nearby galaxies. They stand out from the crowd. Okay, so here we talk about white dwarfs again. Stars collapse until they can't get any tighter. They're only about the size of the Earth. And now it is so-called electron degeneracy pressure that is holding up the white dwarf. So how does that work? Well, it's probably too tempting for me to try and describe it as just the electrons repel each other and refuse to get packed any tighter. It's really more accurate to think of the core now as being so dense, it's really acting like a single gigantic atom. And we already encountered ordinary atoms in the periodic table, and the electrons are only allowed to be in certain quantum levels, the first orbit, the second orbit, the third orbit. And there's a principle that nature has decided to invoke called the Pauli exclusion principle, and that says that you just won't find any two electrons in the same quantum state. You can fit two electrons per orbit, but one has got to have so-called spin up and the other one's got to have spin down. So electrons do have a little bit of a magnetic moment, and they can be thought of as like they're spinning. So you can pack two electrons per orbit. But if the entire star, the entire remnant of the star, can be thought of as one gigantic atom, there's also quantum levels for that atom, about as many now, in this case, as there are electrons. And so when every quantum state is full, there's no way for the electrons to go into a lower orbital. They are already occupying the lowest of all the orbitals in that gigantic quantum object called the white dwarf. So that pressure will hold up the star, and it's not a gas pressure, and therefore the white dwarf will not get smaller as it gets cooler. It'll just stay the same size. So it just sits there and it cools. It can't collapse further because it's held up by electron degeneracy pressure. It can't generate any more energy from nuclear fusion because it can't get hot enough. Can't tap gravitational potential energy. So all it does is it just sits there. Again, we name them because they looked to the early astronomers kind of like the planets Uranus and Neptune. They're greenish. They're greenish because of an emission line of doubly ionized oxygen. But they have nothing whatsoever to actually do with planets. So the planetary nebula phase happens up here as the star has gotten so bloated the outer envelope is now blowing off altogether, and it's revealing the new white dwarf in the center. Okay, so there we go with that. There is the Eskimo Nebula. Looks a little like a planet if you look at it with an old telescope, smaller telescope. And is glowing. This gas has been blown off from the new white dwarf. There's the new white dwarf, the little blue star, not the red one, brighter. This red star is unrelated. It's the little blue star in the middle. That's the new white dwarf. Another one. Hubble Space Telescope shows details of these shells that are blown off much better. The Helix Nebula. And okay, there's one of the brighter ones. This is the Ring Nebula. Brand new white dwarf in the middle. Another white dwarf. There's some galaxies in this picture too, which are in the way, way distant background. 10, 20, 100 million miles away. Whereas this planetary nebula is only about maybe 50 light years away. The Spirograph Nebula, the Eskimo Nebula, Eskimo Nebula again. Doesn't look quite so friendly and Eskimo-like when you've got higher resolution. Looks kind of like an alien. So old white dwarfs, they just slowly cool, but as they cool, then it becomes possible for the carbon to actually crystallize, and of course crystallized carbon is diamond. So we actually do see gigantic diamonds forming out there in the sky. We can see from the vibrations of some white dwarfs, it's telling us that they're transforming into crystalline carbon. Okay, now what happens if we're in a close binary system? Well, then you've got a lot more adventure ahead. So now we've got two stars, and we start out with one star here, one star here. This star is going to be the more massive one, and the more massive one goes through its evolution quicker. We're picking it up here at a later stage. It has already gone through its red giant phase. It has transferred mass. It is bloated out and transferred mass onto this star. And then this star finally goes to being a white dwarf. Now it's this star that goes through its red giant phase, but again there's not enough room to fully become a red giant, so it begins transferring its matter back onto this star. But now this star isn't a regular star anymore. Now it's a very tiny white dwarf. And now the matter is falling down a deep, steep gravitational well. A lot of energy gets delivered. And it falls onto the white dwarf, and it builds up a layer. Now, that layer is sitting on a star, a white dwarf, which is mostly made of carbon. And that carbon, you know, had to be at least 180 million degrees, because that's the temperature that helium fuses to make carbon. However, it's not that temperature on the surface because it was exposed to outer space for a while and cooled off. The stuff that is falling in from this star is hydrogen, mostly hydrogen. Why is it mostly hydrogen? Whoops, I don't know if you guys are seeing that or not. There's an asteroid occultation coming up. I'm going to get rid of that. Be interesting to see where that shows up in my show. Anyway, back to here. So this red giant is going to bloat out and then begin transferring matter onto the surface of the white dwarf. Because the white dwarf beneath the layer is so hot, that layer might eventually ignite, getting up to 10 million degrees. Now, though, instead of being like gasoline inside of the cylinder of a normal engine block, burning very, very slowly and regularly, now it's like gasoline we poured on the outside of the car, and we just put a match to it by making it hot enough to fuse hydrogen to helium. And unconstrained, all that hydrogen will fuse. So a nova happens when a white dwarf collects enough matter from its red giant companion, getting dumped onto it, onto this accretion disk that then settles onto the white dwarf, and the white dwarf eventually heats up that layer hot enough to go through nuclear fusion, and the hydrogen burns to helium all in a flash. Okay, so this is a nova. That's Nova Persei on the right side.